Alright, so in this video I'm going to talk about how we incorporate molar mass and density into the ideal gas law. And it could also be included in the combined gas law, but typically you're going to see it combined with the ideal gas law. So you have to remember that density is a mass divided by a volume. So it's usually measured in grams per liters or grams per milliliters. The molar mass is equal to the mass of that substance divided by its number of moles, or grams per mole. And these equations actually are given to you in the reference sheet under gases. So you're going to see density and molar mass applied in gas law questions. Okay, so let's look at an example. It says that we have 13.9 grams of a substance of an unknown gas placed in a 5-liter container that has an initial pressure at 58.6 kilopascals and its initial temperature at 60 degrees. What is the gas? Okay, so anytime that we're looking for the identity of something, one way to look for the identity of something is to find out its molar mass. So if you can find its molar mass, that's one way to identify a substance. So molar mass is equal to mass divided by moles. So if you have the number of moles and you have the mass, you can figure out the molar mass. So let's pull out the information first. Okay, so it tells me that I have 13.9 grams of some unknown substance. Now, normally, if we're dealing with gas problems in the ideal gas law, you could say that this is the number of moles, but that's only if you know what the substance is. If you don't know what the substance is, you can't figure out the number of moles based on this. So this is just a mass. I have mass, okay? So in order to get my molar mass of the substance, I now need moles. So let's keep reading and see what else we have. We know that the volume of the gas is 5 liters, and it has an initial pressure of 58.6 kilopascals. Even though it says initial pressure, I'm not going to label it as P1. It's not a combined gas law problem because nothing is changing here. It's just giving you a bunch of information. So it doesn't give me a new temperature. It's not asking for the new temperature, so I don't need to assign it a 1 and a 2. All right, so I have my pressure, and I also know that the temperature is 60 degrees Celsius. And again, it says initial. That doesn't matter in this case because it's not giving us a new anything. All right, so that's the information that's given to us. If I want molar mass, which gives me the identity ultimately, I need moles. So I need to know what N is. So I have P, V, and T. I can use ideal gas law to figure out what that is. So let's just check our units. For R, that's equal to 0.0821 liters, atmospheres, moles, Kelvin. Okay. So, well, I'm looking for moles, so that doesn't matter. I have liters and liters, kilopascals, and ATM, so I'm going to have to convert this one. So 1 ATM is equal to 101.325 kilopascals. So if I do the math really quick, I'm going to get 101.325. I'm going to get 0.578 moles. Thanks, Zeus. Okay, so now I need to get my temperature in Kelvin. So plus 273, so 333 Kelvin. All right, so now all my units match, so now I can just plug it into the equation and solve for N. So my P is 0.578, my V is 5, my number of moles is unknown, R is 0.0821, and my temperature is 333. All right, so now I'm just going to plug everything in. So N times 27.33, 0.578 times 5 would give me 2.89 here. Let's divide out the 27.33. My number of moles is about 0.10. All right, so now I have my number of moles and I have my mass. I can figure out what my molar mass is. So, my mass is, 13.9. So now I'm figuring out the molar mass. Divided by 0.057 moles. That's going to be 131.5 grams per mole. Okay, so unfortunately, this question is missing a little bit of information, and that's more of a typo than anything. Basically, if you look at this question, it needs to give you just a little bit more information. It needs to tell you maybe it's a diatomic molecule, or maybe it's a noble gas, or something to that effect. So let's look up the periodic table. Okay, so periodic table, if we look it up, xenon. So this should have told us that it was a noble gas. And it will tell you a little bit more information in the question. Normally that was a typo, my fault. It should be xenon gas, 131 grams per mole. All right, so let's do another problem. All right, so a gas consisting of only carbon and hydrogen has an empirical formula of CH2. The gas has a density of 1.65 grams per liter at 27 degrees Celsius and 734 torr. Determine the molar mass and the molecular formula of this substance. Okay, so first thing, well, we need the molar mass. So we know that in order to get the molar mass, we need grams and moles. So let's pull out the information and see what we actually have here. So we have a density here, which is 1.65 grams per liter. We also know a temperature, which is 27 degrees Celsius, and I have a pressure of 734 torr. All right, so, and that's all it tells us. We just know that we're looking for two things. We're looking for grams and we're looking for moles. We don't have moles, technically don't have grams here, but what I do know is that I have a density, and a density is really a conversion factor between grams and volume, so mass and volume. So really, if I know this, what I know is that if I have 1.65 grams of a substance, of this substance, I have 1 liter of that substance. Well, that actually can give me two pieces of information here. If I set the volume at 1 liter, then my mass should be 1.65 grams. Because if I go measure 1.65 grams of that substance, I should have 1 liter. So I'm going to set my volume at 1 liter. And that also means my mass at that volume should be 1.65 grams. Okay, so now I have my mass. I just need to know how many moles do I have at this volume and these parameters. So I'm going to use the ideal gas law to find the number of moles, because I have a pressure, I have a volume that I set, I have R, and I also have temperature. So now I just need to convert all of my units. So I have 27 plus 273, that's going to give me 300 Kelvin. I'm going to convert this to atmospheres. So convert that, and you're going to get 0.965 atms. All right, and I have liters, I have kelvins. Okay, so now I'm going to plug it in. Everything matches my R unit, which is this. So now I can just plug it into the formula and solve for N. All right, so P is 0.965, V is 1, N is unknown, R is going to be 0.0821, and my temperature is going to be 300. So now I'm going to multiply everything out. N times 24.63. Okay, so divide out the 24 now. So N is equal to 0.039 moles. Okay, so now I've got my moles, and I know my grams should be 1.65 at that volume. So I'm just going to stick it in and solve for my molar mass. So it's 1.65 grams divided by this many moles. Okay, so I'm going to get my molar mass of 42.3 grams per mole. Okay, so now it does ask for the molar mass, but it also asks for the molecular formula. So they like to combine empirical formula into other types of problems like this. So we're going to have to find the molecular formula now. So we know that the molar mass is 42.3 grams per mole. Okay, so I know the empirical formula, give me that. So I know that this is the mass of the molecular compound. So I need to know how many times greater this compound is versus the empirical formula. So when I take this and I get the molecular or the molar mass here, it's 12 plus 2 for the hydrogens. I'm going to get 14 grams per mole. So I need to know how many times greater this is versus this. So 42 divided by 14 is 3. So it's 3 times as great as my empirical formula, which means I'm going to take my empirical formula and multiply it by 3. So my molecular formula should have 3 carbon atoms and 6 hydrogens. That's my molecular formula. All right, let's look at another type of problem. All right, so an amount of an ideal gas at 290.9 Kelvin has a volume of 17.3 or 17.05 liters at a pressure of 1.4 atms. What is the pressure of this gas when the volume is halved and the absolute temperature is multiplied by 4? Okay, so I'm going to pull out the information here. So I have a temperature of 290.9 Kelvin, and I can already see that stuff is changing here, so I need to assign it an initial or a final value. So is it 1 or is it 2? I know that at that temperature the volume is 17. I also know that the pressure is 1.4 atm. So I'm looking for the new pressure here if the volume is halved and the temperature is multiplied by 4. Okay, so you can do this a couple different ways. I'm going to talk about this first. Okay, so if you have your volume and that's halved, your volume goes down by half, so 17.05 divided by 2 would be 8.525 liters. The temperature, if it's multiplied by 4, would be this. So 290.9 multiplied by 4 gives me this. Okay, so I know that I have got variables changing, so I know it's going to be combined gas law. But there's actually a trick to this question, and you don't have to go through all of this to get the answer. So if you really want to, you can totally do that. That's up to you. But a time saver would be to just kind of think about it. Okay, so if you know the relationship between pressure and volume and pressure and temperature, you can figure this out. So you can go through and you can plug it into this equation. We're not talking about moles here, so it would be this equation. And that's totally fine. But I want you to think about this. If I have a volume that's halved, I know that pressure and volume are inversely related. So that means that if volume were to go down, then pressure should go up. Well, if the volume goes down by 2, the pressure should go up by 2. So my original pressure is 1.4. So if I half the volume, or I divide the volume by 2, my pressure should increase by 2 as well. So volume goes down by 2, pressure goes up by 2. So I could multiply this by 2 and get 2.8. And that would be the answer if that's the only thing that was happening. So now we need to think about the temperature, because the temperature is going up. Well, if I know the temperature is increasing, then I know the pressure is also increasing. So if the temperature goes up by 4, the pressure should also go up by 4. So I'm going to take my new pressure here, and I'm going to multiply it by 4. So 2.8 multiplied by 4 would give me 11.2 atms. And this is my new pressure. And if I were to go and plug everything in this equation, I would get the same answer. But I could get the same answer in about 30 seconds if I just kind of think about it. So if you don't see that relationship and that logic right away, then go ahead and plug it in. But this is a lot quicker and a lot less work to me.